Good morning, everyone. So we're going to be talking about MySQL Autopilot. And before that, let me just give a little bit of an introduction. We introduced the MySQL database service with HeatWave last December. And with that, MySQL database service with HeatWave became the only MySQL database service to efficiently process both OLTP transactions as well as complex queries. So what we have with MySQL HeatWave is an in-memory accelerator, which has been designed for the cloud to scale out to thousands of cores. With this, we now have a single database, the single MySQL database, where customers can very efficiently process their OLTP applications as well as analytics. So there is no need for customers to move the data out of MySQL to some other database for analytics. In addition to better performance, in addition to the fact that they don't need to move the data, it is also the case that since the analytic queries or the complex queries are being run on the same data as the OLTP data, OLAP applications also get to query data from the OLTP side of the things in real time. And all existing tools and applications which are compatible with MySQL continue to work as is. Just in terms of a comparison with other similar offerings out there, so if we compare MySQL HeatWave performance with the performance of Amazon Aurora, what we find is for a workload like TPCH 4 terabytes, HeatWave is about 1,400 times faster at half the cost. Furthermore, there is no need to create indexes with MySQL HeatWave. MySQL HeatWave is an in-memory system, and it doesn't need indexes. Whereas with Aurora, you need to create indexes. So we are comparing over here, Aurora fully tuned with indexes and HeatWave without any indexes. And on an average, 4 terabytes TPCH queries, HeatWave is 1,400 times faster, half the cost. So when you look at price performance, it's about 2,800 times. Now, if you look or if you compare with RDS MySQL, again running in the Amazon cloud, what we find is that MySQL HeatWave is about 5,500 times faster at 2/3 the cost. And again, the same thing. With RDS, you need to create indexes for running complex queries, for running analytic queries. Whereas with the HeatWave, there is no need for indexes. So regardless of which database service you're comparing with, MySQL HeatWave is much faster than any other MySQL-based service. And then later on in the presentation, I'll talk about the comparison with analytics services. But compared to any other MySQL-based service, MySQL HeatWave is much cheaper, much faster, and there is absolutely no need for any application change to happen. And this is one of the reasons we are seeing a lot of migrations from AWS and even from other cloud vendors where customers are running their applications on, let's say, Aurora or MySQL in one of these other clouds. And we are seeing a lot of migration of customers to MySQL HeatWave because there is no change to their application. All customers significantly save cost. And depending upon the application, you will see much better performance as well. Now, everyone sees an improvement in performance. The amount of performance the application is going to see depends upon how many complex queries they have and what is the mix of the complex queries versus the OLTP transactions. So the question is that what is it which is so different from an architecture perspective, which makes HeatWave so much performant and so much better? There are four main things. The first thing is HeatWave has been designed from the ground up for the cloud. And by that, what I mean is that as a part of this effort, as a part of the HeatWave team, we have invented and we have implemented new algorithms for distributed query processing. So we have, for instance, take the case of joins, take the case of aggregations, take the case of window functions. We have actually either invented or augmented the existing state-of-art algorithms. And that's what we have implemented in HeatWave so that it can scale to an extremely large number of cores. The second thing is that in HeatWave, we use commodity cloud services. So not only is a system designed and built for the cloud. It is also designed so that it can use the least expensive cloud services so that it improves or it lowers the cost to our customers. So for instance, take the case of storage. We use object store. We don't use locally attached SSDs. And the reason is we want to provide good performance at the least expensive cost. Similarly, networking, we use all standard networking. VMs, we use the least expensive VMs. Right? So we use the commodity cloud services so that we can offer lower cost to our customers. The third aspect is that it has been optimized for the Oracle Cloud. We look at the shapes we are going to be offering the service. We look at the aspects of what is the network characteristics of Oracle Cloud. We look at the storage bandwidth, which we get, and our algorithms have been designed and optimized for the Oracle Cloud. So for instance, based on the cache of the underlying machines, we do partitioning so that each of these partitions can fit in the cache of the underlying VM. Based on the network bandwidth we expect to get in our cloud, we do the optimizer does a scheduling so that it gets an overlap of compute and communication to the best extent possible. So these are the various optimizations we have done in the software, keeping in mind the performance characteristics of the Oracle Cloud. And the fourth and the most important thing is pervasive use of machine learning. We have extensive use of machine learning, both in the server and in the service. And a big part of what I'm going to talk about today is how we are using machine learning to offer value and to offer features to our customers. So the result of these 4 design points is that it results in a service, the HeatWave service, being very performant, very scalable, very inexpensive, and highly automated. So speaking of automation, one of the things which we realize as a cloud provider, as a service provider, is that there's a lot more opportunity for us to automate the applications of our customers than it is on-premise. In the cloud, we have very detailed information about the various real-time metrics. So for instance, we know how much of compute is being used. We know how much of memory I/O are we getting. We know how much of network communication is happening. We know exactly what is the optimization target the customer has. Are they looking for best throughput? Are they looking for best latency? Are they looking for the lowest cost? We know exactly what are the configuration parameters which have been changed and what their values are. Unlike an on-premise system where we have to get this information from the customer, which many times can end up being wrong or something. With the cloud service, we know exactly for each instance what is the value of the configuration parameters. We know exactly what is the software version at the database level, at the operating system level, down to the firmware level. And we know exactly what is the hardware which is being used. So with all this information, we feel there's a lot more opportunity for us to automate the service for our customers. The approach which we have taken for automation is to use machine learning for automation in lieu of rule-based automation. And the big advantage of using machine learning-based automation is that when we come up with the models for automation, these models are specific to a given instance. So it's not the case that, hey, we have one rule or one model which is for all the customers. Each model can be tuned and optimized to a given instance. Secondly, as the workloads change, as the user's application evolves over time, these models can adapt to change without having to reprogram the rules. Third, not only do we make a recommendation of, say, what is the right configuration parameter, but we also make a prediction about what is the expected improvement. So in many cases, there's a trade-off, right? And for instance, data repartitioning is one. We can make a recommendation that, okay, we recommend that you use a different key for partitioning the data in memory. But what makes it a lot more compelling is when we predict what is going to be the expected improvement based on that change. Because then the user can make a determination whether they want to spend some time to do the repartitioning or not, based on the savings they get. And finally, with machine learning, there's an opportunity to provide explanations for these changes, right? As to why is a change being recommended. So the net from all of this is that with machine learning approach towards automation, the system gets more intelligent over time. As you run more queries, as you run more workloads, the system gets better. The query performance improves over time as you run more and more queries. So with this backdrop, what we have recently announced is MySQL Autopilot. And with this, MySQL Database Service and MySQL HeatWave become the only MySQL service which have machine learning based automation. And MySQL Autopilot is offered to all MySQL HeatWave customers without any additional charge. In order for us to do an effective job with machine learning based automation for MySQL, we have enhanced the server significantly in two ways. First, collect new kinds of statistics or new kinds of data, which is necessary for the machine learning models to operate. And the second aspect is to have rich machine learning models. So let's talk about the first bit a little more about collecting data. Typically, when people collect statistics, they collect statistics about the data, right? And a typical way to do that is analyze. What we have done is that not only do we collect statistics about the data, we also collect statistics about the query. So for instance, what is the compilation time for the query? What is the execution time for the query? What is the cardinality of a given operator when a query is being executed? Right? So we are now collecting a lot more metadata about the queries as well as the data. The second aspect is that we have introduced machine learning models for various components of the system. So for instance, we have a machine learning model which models the query performance. We have another one which models the cluster capacity. Similarly, we have a model for network communication, dictionary size, loading of data from MySQL into the HeatWave cluster. So we have various machine learning models for many aspects of the service lifecycle. Now, one of the things to note is that when we have come up with these mechanisms, either to collect new data or to build new models, we have actually augmented the current existing state of art in order to do that, or in order to achieve these good results. So for instance, when we collect data, we have developed, we have invented sophisticated techniques for sampling that we don't just scan the entire data, or we don't sample a static percentage of data. We have techniques which let us sample just the right amount of data so that we sample as few rows as possible without compromising on the accuracy. Similarly, when we collect statistics like number of distinct values, we have actually invented new algorithms at Oracle for statistics extrapolation. So an example is that if you have an NDV on 1 gigabyte of data and your actual data size is 10 terabytes, how do you know whether you can extrapolate from 1 gig to 10 terabytes? Right? So we have actually invented new techniques within Oracle for us to be able to get this accurate information. Similarly, when we come up with these machine learning models for various aspects of the processing, we are using the Oracle AutoML, which was again developed by the HeatWave team. So the idea over here is that instead of having data scientists individually build and train each of these models, we have a completely automated pipeline where you feed in the data, you feed in the task, and it generates a very optimized model. This is one of the reasons we are able to come up with fairly accurate models in a short notice and also do it for a variety of capabilities. So just to give you a quick peek into what AutoML is, it's basically a pipeline which takes in a data set and which takes in a machine learning task like classification, regression, anomaly detection. And what it generates is a fully tuned model. And this tuned model has the best algorithm. It selects the best features, and also it provides the best hyperparameters. And this is all done automatically. This is one of the reasons why we are able to do a much better job than what a human could do in terms of coming with the models for various aspects of the service. So based on this architecture and this technology, what we have in Autopilot are 9 features. And these 9 features span the gamut of the entire service lifecycle. So it's system setup, provisioning. The system automatically makes a recommendation about how many nodes are needed. Then once you have the system set up, the next step is loading of data from MySQL to the memory of the HeatWave cluster. For that, we have these various capabilities which you're offering as a part of Autopilot to figure out what is the right degree of parallelism to load the data, to figure out what is the most optimal encoding so that you optimize the query performance and you optimize the memory usage. Then we have auto data placement, which based on the queries makes a recommendation about what's the right way to partition the data in memory. Once the data loading is done, the next step is to execute the queries. As the queries are being executed, we again have a number of features in Autopilot. We have auto scheduling, which helps us prioritize the short running queries over the long running queries, because majority of customers have a mix of OLTP and complex queries. So in that case, we want to make sure that the complex queries don't end up unfairly like hogging the system too much. So we prioritize the short running queries. Auto change propagation. This is a mechanism which determines what's the right frequency or at what is the right time to propagate changes from the MySQL node to the HeatWave scale-out node. And we'll talk more about that later. Being able to predict the query time prior to a query being executed. This is something which is super helpful for customers to decide whether they want to actually run the query or not, or just to get a swag as to how long a query is going to take. Because many of these complex queries, even though they are significantly accelerated by HeatWave, and even though they are much, much faster than any other service, they could still take seconds or minutes, right? And you may want to prioritize something else. And finally, the auto query plan improvement here, as queries are run on the system learns from the previous queries and improves the execution time of the new queries, which it has never seen before. So that's for the query execution bit. And then finally, in failure handling, the basic idea over here is that without any human intervention, the system is able to detect if there is an issue at the software level or the hardware level and completely transparently recover from a failure without any human intervention. So what I was going to do is to go over in detail on each of these 9 features, followed by a demo. So that's what the structure for the remainder of the talk is. So let's start with auto provisioning. If you go and try any service out there, whether it's Redshift or whether it's Snowflake, the onus is on the application to determine what is the right cluster size needed for a given workload. And this is usually not very easy to do. And even if you get it right the first time around, as the workload changes very soon, you will end up with a cluster size which is suboptimal. So either it's too large or it's too small. And it's not easy for people to determine what's the optimal cluster size. What we have is a feature called auto provisioning. The only input that is needed to auto provisioning are the tables on which you want to run analytics. When the user provides the names of the tables, the system automatically scans these tables in an intelligent manner. So for instance, if you're giving it a table of say 4 terabytes, it's not going to scan the entire 4 terabytes because that will take a long time. It will scan a very small percentage of the rows. And for most of the real world applications, what we have seen is that auto provisioning is able to come up with a very accurate estimate by sampling 0.01% to 0.1% of the rows, right? So it's a very small fraction of the rows. And it does this intelligently so that it samples only the bare minimum number of rows. And based on that, the system is able to predict 2 things. A, the amount of memory that will be needed for storing this table in memory, because HeatWave is an in-memory system. And B, how much of memory is needed for the intermediate results. Based on these 2, the system is then able to predict how many nodes are needed for the HeatWave cluster. So what I'm showing over here is for a variety of data sets, both industry standard benchmarks as well as customer workloads, the system is able to predict the memory usage to a very, very good degree with a very high accuracy, right? So pretty much it's always been close to 97%. And this is all done by scanning less than 0.1% of the data. So we scan a very small percentage of the data. Using the machine learning models, we predict what the memory usage is. And once we know what the memory usage is, we are able to determine how many nodes are needed in the heatwave cluster. Now, this is something which is exposed, available as an advisor. So the system will make the recommendation. But as the user, you have the complete latitude in overriding that, because you may want to plan for the future and you may say, no, I'm going to go with a larger cluster size because what the system is telling you is what is the smallest cluster size, right? But you may decide to override that and go with a larger one. So it's something which is exposed as an advisor. Now, once you have provisioned the system and you have a heatwave cluster attached to the MySQL database, the next step is to load the data from the MySQL database into the heatwave cluster. Now, as you load the data into the heatwave, for each table which is being loaded into the heatwave cluster, you can specify a degree of parallelism. Now, the higher the degree of parallelism you have, the better the performance is going to be. It'll take less time to load with a very high degree of parallelism. But the downside of always having a very high degree of parallelism is that it can lead to memory fragmentation, which increases the need for the memory. So what auto parallel load does is that based on the tables, when it does the scan, it determines what's the optimal degree of parallelism per table so that you get the best performance and also you get the lowest memory usage. So what I'm showing in these results over here for these three customers, if you look at the right-hand side, with Autopilot, we are still getting the best performance as we get with the highest thread count. So what we're comparing with is a thread count of 32 threads. With Autopilot, we get about the same performance, right? So we're not compromising on the performance. But what is interesting or what is improved is what is highlighted in green. The memory usage both on the MySQL node side as well as on the heatwave cluster side is reduced, right? So on the MySQL side, you can see for all the three customers, the memory improvement is anywhere from 25% to 60%. On the heatwave cluster side, it is less, but still in the first case, for instance, there's a saving of up to 20%. So what we find is, and this is happening because as we are loading data from MySQL into the heatwave memory, per table, the system determines what is the least amount of parallelism such that it doesn't compromise on the load time, but it minimizes the memory usage. Now, the third feature is auto-encoding. Now, by default, when we load data into the heatwave memory, we use the encoding of variable length. The advantage of using variable length is that you can run all queries. So if you have, say, an operation like, that requires the data to be present, right? Like represented as variable length in the heatwave memory. But the downside of the variable length is that it takes up more memory on the heatwave cluster. An alternative is to use dictionary encoding. With dictionary encoding, you reduce the memory size on the heatwave cluster, which means it reduces the cost to the user. Because if you're taking up less memory, it means you need fewer nodes of heatwave, which means lower cost. So if you use dictionary encoding, you can have a smaller cluster size of heatwave. However, there are certain queries which cannot be processed or which will take a much longer time. So in order to make this optimal decision, we have introduced auto-encoding, where the system looks at the queries or the workload, and based on that determines which of the tables or which of the columns should have a dictionary encoding and which of the columns should have a variable length encoding. So that way, you get best of both the worlds. You're still able to execute all the queries. You still get the best performance, but you use up the least amount of memory between the heatwave cluster as well as the MySQL node. It is also possible that in some case that the amount of memory being requested on the MySQL node, because that's only one node, is very large. And that's the other trade-off which the system is going to make for you, right? And say, hey, you know what? You can't use dictionary encoding because the system is going to not have that much of memory on the MySQL node side. That's why that column should be represented as variable. Right? So all these trade-offs and optimizations are done by autoencoding. The fourth feature is auto data placement. So if you take any clustered system, when you run queries on a clustered system, one of the very important parameters which influences the performance of the system is the data distribution. So if you have placed your data on these various nodes in such a manner that when a query comes in, that query will lead to a lot of data movement between these nodes, the performance of the system is going to suffer. So we want to be in the situation where the data is distributed in such a manner that we minimize data movements between nodes. So a good example is that if you have a join on a given column, and let's assume hypothetically that all the queries are doing a join on the same column, you want to make sure that across these various nodes, the rows which had the same key for that column are co-located. Right? So two tables which are being joined on a given column, if you co-locate the keys with the same value on these various nodes, then you know that when a join happens, it can do the processing all within a node, and there is no need to move the data between the various nodes. Similarly, for other operations like aggregations. Now, you can do it for a few queries, and if the things are simple. But as applications get more complex, for most of the real-world applications, there is a combination of multiple operators, multiple columns, and what the system is able to decide with auto data placement using machine learning model is that which data distribution is going to give you the best performance. So what the system does is that it looks at the queries which you've been running, it looks at the current data distribution, and then makes a recommendation if you're going to save time by altering this data distribution. Not just that, it also makes a recommendation or a prediction as to how much of time are you going to save if you follow that recommendation. So the system tells you what is the new key which the system recommends on which you should partition. And secondly, it tells you how much of time you're going to save. And based on that, the user or the application can determine if they want to follow that recommendation or not. Again, for a whole bunch of use cases we have seen that we always make, Autopilot always makes the right recommendation. And we are working on improving how good or how accurate our prediction is of the amount of improvement. Right now, we understate it, and it's something which we're going to improve over time. So with this, we complete the phase of loading the data into the HeatWave cluster in an optimal manner. Right? So the first step was provisioning. So we provision the cluster optimally. Then the next phase was these various techniques or various features to load the data optimally into the HeatWave cluster. Now we come to the next phase of the service life cycle, which is running the queries. One of the most compelling things which we introduced is the auto query plan improvement, which works as follows. When a query is executed, on the left-hand side, what we are showing is we have A join B, join C. As queries are executed, the system learns from the queries which are being executed and stashes away some information. So for instance, in this case, the system is going to stash away information about the actual true statistics of columns A, B, and C. Because when it has executed the queries, it has scanned the column A, so it knows exactly all the information about column A. Similarly, the system will also stash away intermediate results, for instance, of or the statistics of the intermediate results, right? Of A join B, for instance, like what was the size of the intermediate results. Similarly, for A join B join C. In the future, when a query comes in, which it has never seen before, the system determines if it can reuse some of the information it has collected for executing part of the query. So on the right-hand side, what we now have is A join B, which is then doing a union with D. The system has a very accurate information about A, B, and A join B. It reuses that information, and it does the best estimate it can for column D and for the union operator. So what now has happened is that when we ran this query on the right-hand side, the system was able to get some information from the previous query, which is not related to this query directly, and improve the performance. And when I say improve the performance, it can improve the performance in two ways. The first way it can improve the performance is, since it has better statistics, it can come up with a better execution plan. The second thing is that at runtime, for instance, when we are deciding on the size of the partition, based on the information it has, which is a lot more accurate, it can actually help with, say, the sizes of the partition or with the data distribution. So it actually improves the execution time itself. No other database offers this feature. And just to give an example, when we ran TPCH and TPCDS on 24 terabytes with Autopilot turned on, it improved the performance of the system by 40%. Same data, same query, same size of the cluster, the performance improved by 40%. So what it means is, from a price performance standpoint, or if you're paying by the hour, your cost just went down by 40% by this feature alone. The next feature which we have added for query execution for Autopilot in Autopilot is query time estimation. To start off with, what we have is we have an analytic model for our query processing algorithms. There are a lot of aspects of, like, HeatWave, which are very novel. And one of the aspects is that we have a lot more deterministic query execution model. And based on that, the first estimate we come up with is fairly accurate to begin with. So a user, let's take the case of the query one. The user tries to predict the execution time of query one. The system is going to tell you some value. When query one has executed, the system knows exactly what it was correct, right about, and what it was not. Secondly, after the query is being executed, it has a lot more information. For instance, it has runtime statistics. It has information about the cost profiling. So based on all of this information, if I want to do an estimation of the query of the execution time of another query, which is shown over here, like say in query 2, the system will do a better job. This is another example as to how the prediction we are making for the query time improves over time as more and more queries are run on the system. The system learns from them, the system gets more intelligent, and improves upon them. The next feature which we have in Autopilot for query execution is auto scheduling. A large percentage of real-world applications are mixed workloads, which means they have a combination of short-running OLTP transactions and some complex queries. What the system does is that, first of all, like I just showed in the previous slide, the system predicts the time it's going to take to execute each query, which has been scheduled. And then, instead of using a FIFO mechanism, the system prioritizes the short-running queries over the long-running queries. Now, you don't need to worry about starvation in the sense that it's not to say that if you only had short-running queries and the short-running queries keep coming in, that the long-running query will never get executed. You don't have to worry about that. That the scheduler takes care of. But in general, the system will prioritize the short-running queries over the long-running queries. The benefit of doing this is that if you take the case of like most of the real-world workloads, which have this combination of short-running and long-running, the improvement in the overall runtime for the query, right, which is a combination of the wait time and the execution time. So the total elapsed time for these short-running queries improves dramatically, whereas the impact on the longer-running queries is marginal. So please note, the overall execution time for the system or for the queries is not changing. That's the same. So it's not to say the system is getting smarter. The thing which the system is doing is it's doing a smarter job of scheduling so that the wait time of the queries is reduced. of the short-run inquiries, so that the total elapsed time for the short-run inquiries is significantly lower. So, and this is an example. In fact, these are queries from TPCH, and you can see that the short-run inquiries got prioritized and they improved significantly, whereas the longer-running ones had a marginal hit in the overall elapsed time. Now coming to the last feature of the query execution in the autopilot is the auto change propagation. So one of the things which we mentioned when we did the launch for MySQL HeatWave is that anytime you make a change to the MySQL database, that change is propagated in real time to the memory of the HeatWave cluster. So anytime there's a change made to the MySQL database, that change gets propagated into the memory, so that if you have a query which comes in soon after this change is made, your queries will get to see the latest and greatest results. That's one of the very, very marquee features of MySQL HeatWave, right? That it's real-time analytics. Customers always see the latest and greatest results after a change has been made. What we are now talking about is that we have introduced this HeatWave storage layer, which keeps a copy of the in-memory representation in the object store. Now, this change, but when a change is made in the MySQL database, it's propagated to two things or two places. One is to the HeatWave memory, and that happens instantaneously. The other is that this change is also propagated and persisted in the object store. This happens asynchronously. Now, the frequency at which we make this change to the object store is determined by a machine learning model, which factors in a variety of aspects. It factors in how many changes have gone in, what is the rate of change, what is the size of the change, what is the kind of DML, what is the object store bandwidth which is available. It takes all these parameters into consideration and then determines what is the right time to propagate the change from the memory of the HeatWave cluster to the object store. Because there's a trade-off. If you push the changes too often, you're taking some impact, both in terms of compute as well as the bandwidth. Whereas if you do it at the appropriate time, you don't take up so much of computation on the cluster. At the same time, you know that when you need to reload data from the object store, you don't need to do too much of a computation to coalesce the results. Again, as far as we know, no other system provides support for machine learning-based change propagation. And finally, the last phase of the service lifecycle is error recovery. There could be a variety of reasons for which the system could have an error. The error could be because of software problem, or it could be because of a hardware problem. Regardless of what the problem is, the system detects that there is an issue. It automatically takes the corrective measure. And once the corrective measure is taken, which could be either restarting of the failed node or reprovisioning of the node, the data is reloaded from the scale-out storage completely transparently, and the system is back online. Now, one thing which is important to point out is that while the error recovery is going on, and although it's fast, the MySQL database service is always available, right? So any queries which come in, they will still always be executed by the MySQL database service without any issues. So at this point, what I'm going to do is I'm going to show you a demo. And what this demo is going to show is how we are using some of these features of Autopilot, which I talked about, and how they can be used. So I'm going to play this.
With the first feature, which is auto provisioning. So for that, we are going to log into an instance of the MySQL database, which has 4 terabytes of the TPCH data loaded. The first step is to determine what's the right size of a HeatWave cluster. For most of the services out there, the onus is on the application to determine what's the optimal cluster size. With MySQL Autopilot, users can invoke the MySQL advisor, and this advisor, the only input that is required is the schema or the table on which you want to run analytics. So we're going to select the TPCS schema, and the system tells you very accurately how much of memory is going to be used and what is the size of the cluster that is required. This is fairly interactive, where you can go and deselect some of the tables if you want to see what change will it make in terms of the recommendation. So when we deselect the line item table, which is the largest table, you see that the size of the cluster reduced from 12 nodes to 4 nodes. But since we are going to be using TPCH as the working example, we're going to go back and select the entire TPCH schema. And the system is recommending that we create a cluster of 12 nodes, and that's what we're going to do. And with this, now we are provisioning a MySQL HeatWave cluster with 12 nodes per the recommendation of auto provisioning. Once the cluster has been provisioned, the next step is to load data from the MySQL database into the HeatWave cluster. So for this, we're going to invoke the AutoLoad Advisor. The AutoLoad Advisor does two things. The first is, based on the data which is going to be loaded into the HeatWave cluster, it determines how much of memory is required on the HeatWave cluster and how much of memory is required on the MySQL node. And if it turns out that the memory requirement is larger than what the system has, it's going to issue a warning before the load starts. The second thing is, for each of the table which is going to be loaded into the HeatWave cluster, it determines what's the optimal degree of parallelism. The optimal degree of parallelism is such that it minimizes the load time, at the same time minimizes the memory requirement. So what you will see over here is that for the line item table, it's picking a degree of parallelism of 32, and for the nations table, it's picking up a different degree of parallelism. Once the data has been loaded into the memory of the HeatWave cluster, this loading is done based on the primary key. So the primary key is the default key on which the data is partitioned in the memory. Based on this partitioning, we run the 22 TPCH queries, and we see that with this default partitioning, it takes about 18 minutes to execute the queries. We're now going to invoke the Auto Data Placement Advisor to see what recommendation it has. When we invoke the Auto Data Placement Advisor, the Data Placement Advisor makes a couple of recommendations. The first one is, it recommends if any of the tables which have been loaded into the memory need to be altered and repartitioned based on some other key. So in this case, it's making a recommendation that the line item table and the part supplier should be partitioned on a different key. The second thing which the advisor does is to predict the amount of savings you're going to get if you partition based on the new key. So the system is telling us that we're going to save 5.5 minutes if you follow the recommendation, and we're going to follow the recommendation and we execute the command to alter the partitioning in memory. Once the data has been repartitioned based on the new key, we are going to run the 22 queries again and see what the performance is. When we rerun the queries based on the recommended partitioning scheme from Autopilot, we see that the query time dropped from 18 minutes to 8.5 minutes. Now that we have the optimal partitioning in memory, the fourth feature I'm going to show for Autopilot is the Auto Query Plan Improvement. So for this, I'm going to connect with two different sessions. In the first session, I'm going to run query 1, which is derived from one of the TPCH queries, and we're going to run on a fresh instance of the database. When we run query 1, it takes about 2.5 minutes to execute query 1. And there is no history on this instance of the database. Now from another session, I'm going to run a different query, slightly different from query 1, which I'm calling query 2. Query 2 has some similarities with query 1. So for instance, it's selecting from the same set of tables. It has some common predicates, but it also has some differences, like it has some different predicates as well. When we execute query 2, the system learns from the execution of this query. For instance, what was the size of the intermediate results? So the system learns from the execution of query 2. And then when we run query 1 in session 2, it is going to come up with a better execution plan. So now when we run query 1, we see that there is a significant improvement in performance in query 1's execution. The execution time dropped from 2.5 minutes down to 30 seconds. And this is because of the autopilot, which is turned on by default.
Okay, so that was a demo, and there we were showing like the setup was a 4 terabyte TPCH benchmark. And again, you can try it on your workloads, and I think the results are going to be fairly similar, although the mileage varies based on the data size and the specific workload. Now, with autopilot turned on, which is now turned on by default, what I want to show you is that what is the impact this makes. So in the beginning, I was showing you comparisons of MySQL HeatWave with RDS MySQL and Aurora, which are like, think of them to be like, general purpose databases. Now what I'm showing over here is a comparison of MySQL HeatWave, where MySQL HeatWave does both, right? It does transaction processing and analytics. It's a general purpose database, comparing with the performance of databases which are specialized for analytics: Snowflake, Redshift, Azure Synapse, and Google BigQuery. And this is 30 terabytes TPCH. MySQL HeatWave is the fastest database compared to any of these competitor services, and also the least expensive one. So on the left-hand side, right, you can see like both the geometric mean, which is the average time it takes to run the workload on any of these four other databases, and HeatWave. And HeatWave is 11.4 seconds. Everyone else is much higher. And then what is also shown is the actual dollar cost. Because for many of the customers, it's not just about price performance. They also want the lowest cost, absolute lowest cost, because if they're going with an annual subscription, they want to get the least cost, even though the performance may be at par. And what is very compelling about MySQL HeatWave is that it's the fastest service and also the least expensive. And on the right-hand side, you see what is the compounded benefit of price performance, right? So compared to Snowflake, MySQL HeatWave on 30 terabytes TPCH is 44 times better price performance. Compared to Redshift or compared to Synapse, it's 15 times better price performance. And compared to Google BigQuery, it's 37 times better price performance. And none of your tools and applications which work with MySQL need to change. And you don't need to move the data to a different database, right? So all the benefits of having a single database, right, they exist with MySQL HeatWave. Plus, it's so much faster. Plus, it's so much cheaper. And a lot of these is because of the autopilot capabilities, which have made a huge impact in the performance. And as I was saying, on 24 terabytes, just based on one feature, auto query plan improvement, we saw 40% improvement with the performance of MySQL HeatWave. Now, this was for analytics. Now, since we have gone GA, we've had a lot of customers migrate their production workloads from AWS, Aurora, and are now production with HeatWave. So a good example is Red3i. They moved a 6 terabyte workload from Aurora to MySQL database. And what they found is with HeatWave, their costs dropped by 60%. So now they're paying 40% of what they were paying with Aurora. Many of the queries improved by 1,000 times, right? So these are queries which pretty much would take forever on Aurora. In the net overall aggregate workload, which has a combination of short running and long queries, right? Overall workload improved in performance by 85% with MySQL HeatWave. Right? So the queries which take long time, the complex queries, they improve significantly. The less complicated queries improve less. And just the OLTP transactions, they are at par. So overall 85% improvement at 40% the cost. And no change to the application, right? Because Aurora is API compatible with MySQL. Another example is Tetris. Very similar story. Their cost reduced to less than half as they migrated from Aurora to MySQL HeatWave. Migration was seamless. They have a mix of OLTP analytic queries, and their query times reduced from minutes to milliseconds. And what they say is that they can run new classes of queries. They can run, their customers can run new kinds of reports and new kinds of applications which they could not earlier with Aurora, right? At half the cost with MySQL HeatWave. Fan Communications, very similar story. As they migrated from Aurora to HeatWave, cost dropped to less than half. Performance, net aggregate performance of the compiled workload, which has a combination of short running and long running queries, improved by 10 times. Right? So half the cost, 10 times improvement in performance, and they could do this without modifying their application. Similar story at Tamara. Right? Their cost dropped by 3 times. So it's 1/3 the cost. The queries accelerated significantly. And as they quote, they can now enhance their application by writing more complex queries. Their application logic can become richer because earlier they were not able to do it. Right? And now with MySQL HeatWave, since the system is so much faster, they can actually write queries which are important to their customers. So to summarize, with MySQL Autopilot, which is offered at no extra charge, we have support for machine learning-based automation. And with this, the MySQL database service becomes the only MySQL-based service to offer machine learning-based automation. It automates the entire service lifecycle from provisioning, data loading, query execution, and failure handling. HeatWave was already much faster than Redshift and other competitive database services. But with this recent announcement and recent capabilities, in particular Autopilot, the performance has improved further. So a performance advantage, the performance difference of HeatWave compared to other services got even wider. And HeatWave continues to be the fastest service and also the least expensive service compared to other competitive analytics services. As a next step, we really encourage you to try what you have heard, what you have seen so far yourself. And for this, you can get $300 of free credits, which you can try for 30 days. And Autopilot is enabled by default. You can also follow us and connect with us at various forums, Twitter, Facebook, LinkedIn. And if you would like more information, we have a lot more details on our website. So with this, I'm happy to take any questions.